Traversal. This is Ashwin Muthraman again here. So the next lecture is on the next type of traversal, which is called the breadth first search. Now we have this BFS algorithm here, and this is one of the graph traversal types. We would have already studied this in the tree traversal, but then this is also for graphs. So what's the main difference between DFS and BFS is that in DFS we already saw there is a implicit recursion going on. So now here we are going to change. Implicit recursion means it uses stack by default, right? Recursion uses stack by default. Now whenever there is a stack, there will always be an alternate to it, which is called the queue. So instead of implicit stack, we are going to explicitly use a queue data structure here and then try to traverse the graph fully. Now again, the breadth first search is like this. Here the algorithm, so the visited array, the same reason, because if a particular node is visited, we should not be keep repeating it, because that goes into an infinite loop. To stop that, we need a visited array which is 1 to n and which is initialized to 0 initially. Now BFS algorithm starts like this. So here visited of v is equal to 1. So initially at whichever node you are, you are visiting that node. So we will make that as visited is equals to 1. Sorry. Now initialize the queue. So we have a queue that we are initializing with this vertex. Okay. So the queue will initially be empty. First, what you are entering, right? You are entering a particular node and insert that node into the queue. While that queue is not empty, right? While the queue is not empty, what we are going to do is delete the queue. Delete one element from the queue, that is pop one element from the queue and then pop an element from the queue, right? You will delete it from the top, the front element, and then you can print it here if needed. So yeah, I'm just putting a line here. Printing can be done, right? Print after deleting that element, you can print that element for the sequence that will come with an example here. Now for all the adjacency, same like that, for all the vertices adjacent to V2, if visited of this is equal to 0, then what we did there, we called a recursive function in DFS. Now we are not going to do that. We are going to add that element to the queue and then make the visited of 1, so that no other adjacency vertex will take this as again into its list. Okay, we'll make the visited as 1 and end the for loop here. So if you delete an element, you take that element, you traverse all the adjacency vertex of that and then just add it to the queue. You're not traversing that, just add it to the queue, make the visited 1 and then just end the loop here. So for each of the vertex that you have in the queue, you just pop it out, you just add it and then that's it, done. So now until this queue is empty, because we are adding few elements here, right? It keeps on going until the queue is empty. You just come out of the loop. This is the BFS algorithm. Let us go through the same example that we have discussed with DFS. Now here the queue is initially empty. So now let me take the first node as 1 and the visited array is to be 0 in the initial cases. Now let us go into 1. So the first thing is visited of v is equals to 1. So visited of this should be 1, right? So I'm just making the visited of this to be 1 here. So this is a visited array, like I'm just keeping it like this. We're not disturbing any other thing, right? Now visited of this is 1. Initialize queue with vertex v. Yes, I'm initializing this with 1 in step number 1. Now what we are doing, while queue is not empty, do deletion of queue. Now this is the sequence that I'm writing here. I can print the element here. I have deleted it from the queue. I am printing that element. So 1 is gone. I'll just put a mark here. 1 is deleted. Okay. Now for each of the W adjacent to V. So what are all adjacent to this? 2, 3 is adjacent. Now I popped out this. Now for 2 we have to go and see visited is 0. Yes. Now add it to the queue. Now add this to the queue and then make the visited as 1. Now for the next adjacency thing, 1 is 3, right? So add it to the queue and make this as 1. Because there are 2 vertex adjacent to 1. Now what we have to go for each of them, if the visited was 0, make the visited as 1 and then add it to the queue. That's it. These are the 2 steps that you have to do. Now this is the queue. Next step queue. Now this loop has ended for the first element. Now for each of the element until this queue is empty, right? So again we will go. So the next step what will happen is queue will be like this. because I've deleted 2, so this will be out of context here, so it will come out as 2. Now there will be 3 in the queue and then the neighbors of 2. So now go to the neighbors of 2. 1 is a neighbor, but then this condition is not satisfied. 1 has already been visited, so we are leaving that. Next, 4 is a neighbor, 5 is a neighbor. There are only 3 3 edges from 2. So we are considering 3 neighbors. 1 is already visited. Now we are going to visit 4. So now if you go to 4, 4 is adjacent to 2. Yes. So if visited of 4 is not yet done, make the visited as 1 and then add it to the queue. So now I am adding 4 to the queue. I can also add 5 to the queue because that for loop is not ended here. 1, 4 and 5 are there in the for loop. 1 is already visited, 4 we have just now visited, and then 5 also I'll add it to the queue. Okay. So this is the current state of the queue. Now the for loop has ended, but the while loop did not end. So now while queue is not empty. What we have to do, we have to pop one more element out of this. Now pop this. Now how the queue will be looking like is 4 is the first element, 5 is the next element. Now 3 has been popped out. So once it is popped out, I can write the output sequence here. Right? In step number 3, what has happened is 3, 4 and 5. Now we are deleting 3. We need to go for the edges of 3. Now 1 is there, 6 is there, 7 is there. Right? So now 1 is already visited. This condition will fail. Now we are going to check 6 and 7. Is 6 being visited? No, 6 is not yet visited. So I'll just make 6 to be 1 and then add it in the queue. This is for deleting the element 3, right? And then 7 is also not visited. Just make this as 1, add it to the queue. This is how the queue looks like. Now this for loop has ended for the third element that we have printed. Now go back to while queue is not empty. What will happen? Now I am deleting 4. I am just writing 4 here. So it will be 5, 6, 7 and then like this. Now for the element that we deleted, we need to look at the adjacency list, adjacents of that. 2 is already visited array, this condition fails, so I'll go out, and then again 8 is there. So now 8 visited is equal to 0, yes. So I'll just add it to the queue and then make this as 1. Now what will happen? Now I have to delete. This loop ended, but then the while loop did not end. Now for the F condition, what we will do is queue. I'll just delete. So this is the current status of the queue because I'm going to delete 5. I'll write 5 here. So for 6, if you see, there are only 3 and 8, which is already visited, so we cannot do anything. So I'll just delete 6. If you delete 7 also, what will happen? 3 and 8 already visited, we cannot do anything. I'll delete 7 as per the queue order. For 8 also, 4, 5, 6, 7, everything is visited, so we cannot do anything. We'll just output 8. So this is where the sequence comes. This is the BFS. If you order the graph and see, at every breadth level, we have the sequence printed like this: 1, 2, 3, 4, 5, 6, 7 and then 8. Okay, so this is why we call it as breadth first search level order traversal. This is also called as level order traversing, so you can go by level. So this is why the output sequence is printed like this. Now coming to the time complexity, which is already defined in the BFS, which is the same, because if you use the adjacency matrix for each of the vertex, finding the adjacency here. So this for each of the vertex, anyways, each vertex should be traversed, right? So it's going to be order of n squared if you use adjacency matrix. And if you use adjacency list, it's going to be order of 2e, which is like, because 2e is the number of nodes in the vertex, right? So basically you're using a list, but then again e is again composed as order of n squared, because the maximum value of e is defined as n into n minus 1 by 2, which is order of n squared. So time complexity is n squared. The space complexity, we don't have any improvement here. Time complexity is also same as depth of first search. Space complexity is also order of n, because we are explicitly defining a visited array and we are explicitly defining a queue. Queue size will not exceed the number of nodes, right? Because that's what the algorithm has been designed for. So this is order of n. Thank you.